There's no change. Better? Excellent. Okay, so yeah, thank you to the organizers for having me here and for starting us off with this wonderful summer school portion. A lot of you have done some exercises that I think will be directly relevant to this talk, so hopefully that helps you out. But yeah, we're interested in studying these cohomology rings of generalized Grassmannians, and in particular of flag varieties. And what I think a lot of us in this room really, really want are some rules for telling us how to multiply in a combinatorial way. So today I'm going to tell you about one special case of such a rule that's applicable for inverse Grassmannian permutations. Okay, so we'll start with a brief recap, just so notationally we're on the same page. So first of all, Schubert polynomials. Really, we're interested in studying these Schubert structure constants. And so we have Schubert classes in the cohomology ring of the complete flag variety, and they form a linear basis. And we can take two things in this basis, we can multiply them together, and we can expand them out again in the basis. And these structure constants that we get are called Schubert structure constants. And we know for geometric reasons that they are non-negative integers. And so combinatorially, we always hope that they're going to be counting something or telling us, yes, something about like a combinatorial set. So if you would rather work algebraically instead of in the cohomology ring by Borel's isomorphism, we have this presentation of the cohomology of the complete flag variety as a quotient of a polynomial ring. So we just have a polynomial ring in n variables, and then we're quotienting out by the ideal generated by the non-constant elementary symmetric polynomials. Another way to think about this with maybe too many generators, so many generators, is symmetric polynomials, which have no constant term, will generate this ideal. What's that? Oh no, it's because in the introductory lectures, I was using like k as the number of variables, and then I think that lingered. It should definitely be an n. Thank you, Frank. Absolutely, yeah. Okay, hopefully I get back to n land now. So yeah, Schubert polynomials are a special family of polynomials that are coset representatives for the images of the Schubert classes under this map. So we could have potentially lots and lots of coset representatives, but Lascaux and Schutz and Berger told us, well, these polynomials are particularly nice choices for these representatives. Okay, and in particular, they satisfy a lot of nice properties. One of them is the stability property. So there's natural inclusions of one symmetric group into another symmetric group. We just take the permutation that we had if it was in Sn, and we just throw like an n plus 1 at the end of the string and then think about it as a permutation in Sn plus 1. So it's a fact that the Schubert polynomials are stable under this inclusion. So we can really think about them as being indexed by permutations of positive integers. And these, in particular, these permutations, you want them to have a finite number of non-fixed points. So basically, you can think about them as living in some finite symmetric group that's large enough, but they're all playing nicely together in this much larger place. So with this sort of inclusion and thinking about Schubert polynomials as now being indexed by permutations of z plus, we get a basis for the for this ring z adjoin x1, x2, this limit of polynomial rings. And then, well, we have a basis. We can take two basis elements. We can multiply them together. We can expand. And what we get here are really these same coefficients. Whenever u, v, w are all living in the same symmetric group together, then it's the same thing you would see from the cohomology of the corresponding flag variety. So we can do computations up here with Schubert polynomials and their corresponding combinatorics to help us understand the structure of the cohomology ring of the flag variety. Okay. So yeah, then we want combinatorial formulas to help us understand these coefficients. One like major success story is the Grassmannian permutations. When you have a Grassmannian permutation, your Schubert polynomial is just a Schur polynomial. I think you were asked to show, or I know you were asked to show this in the exercises, so maybe a lot of you know this well by now. And we have just an explicit rule in terms of certain fillings of tableau. When you have Grassmannian permutations, their natural indexing things are really partitions, and so we can play some partition combinatorics, and we can just count types of objects that we get that satisfy certain constraints to tell us what these structure constants are. So this sort of rule is really the gold standard, the thing that we would hope for more general situations, like the complete cohomology ring, instead of the special subring. Okay, so what we're going to focus on today, instead of Grassmannian permutations, we're going to look at inverse Grassmannian permutations, which is just what it sounds like. It's the inverse of a Grassmannian permutation. So a Grassmannian permutation has at most one right descent. An inverse Grassmannian permutation has at most one left descent. What this looks like in terms of strings, you can see this example here for 1, 2, 5, 6, 7, 3. We're looking for adjacent values that are, adjacent numbers like 3 and 4 are out of position in this string. And so since they're out of position, it doesn't matter that they're far away. We have a left descent at position 3. So I would say that this permutation here is 3 inverse Grassmannian. Okay. So another way to think about this is we're taking the string 1 through 3 and the string 4 through 7, and we're just kind of shuffling them together in some sort of way. Okay. So these will be our main permutations that we want to think about what happens when we multiply the corresponding Schubert polynomials. Now, Weiser gave a combinatorial rule for multiplying certain pairs of inverse Grassmannian Schubert classes. Weiser's strategy was to study GLP cross GLQ orbit closures on the complete flag variety and look at their associated Richardson varieties. And so he was able to use these techniques, and in particular extract combinatorics in terms of objects called PQ clans to understand the situation when, again, you have pairs of inverse Grassmannians that are satisfying, we'll see, maybe slightly restrictive conditions. So let's take a look at what goes into Weiser's rule. So first of all, we have to talk about what are these PQ clans. Okay, so clans, it's just a fancy way of saying that we're having a partial matching. So usually we have a P and a Q floating around, so a partial matching on 1, 2, up through P plus Q. And then the unmatched places, they have something special going on. So they either get assigned a plus or a minus. And then we want this funny condition that the number of pluses that we have minus the number of minuses is P minus Q. So if you have an object like this, then this thing is called a PQ clan. So it's very convenient with matchings to just kind of draw arcs saying, well, 2 is matched with 4, and so that's what this visual representation is doing here. And then I just put the signs that go with the unmatched numbers. Now, there's a particularly special clan for each P and Q that Oliver and I like to call the rainbow clan. Oh, I should have said it was on the front slide, but this is all joint work with Oliver Pachenik, who's somewhere up there. Okay. We like to call this thing the rainbow clan. So for any P and Q, there's a unique rainbow clan, and I'll just tell you kind of in visuals what this is. So the very middle of the clan is some consecutive sequence of signs that are all the same sign, and that'll be governed by what P and Q are. And then surrounding that interval of signs, we'll have just things matched up, and it literally looks like a rainbow. So there's not going to be any crossings. It's not going to be shifted in any weird way. It's just these things here. So are there any questions about rainbow clans? Okay, so these are kind of like our target. We're going to take other clans, and we're going to try, yeah. No, you have to have all the same sign, yeah. So it has to be all pluses or all minuses. They're going to be centered in whatever your interval is, and then in the other places, you just have these nested matchings. Yeah. So our goal is always to take a random clan and kind of move ourselves towards rainbow. And we're going to do this with certain local moves. So there's a lot of moves, and I'm going to show all of them to you. But the big picture idea for all of these moves is that we're doing little swaps that are bringing us closer to being rainbow. And we're doing these swaps at a particular position. So they're going to do something with I and I plus 1. Yeah. Mm-hmm. No, the signs all have to be a consecutive interval on the inside. This is why I should have like written the definition instead of just pictures. But yeah, so consecutive interval all in the middle, and then arcs around it. Mm-hmm. And for instance, when P equals Q, we need just there to be no signs at all, and so it really just is like a rainbow. Yeah. But then these other ones, when P and Q are out of balance with each other, then there will be some leftover signs, all the same sign, that land in the middle, inside the rainbow, like a pot of gold or something. Although maybe this one, like you owe money because there's a bunch of minus signs, but okay. So this is our target. We want to get to the rainbow. So these moves on clans, there's a bunch of different types of moves, but they're all acting kind of locally at I and I plus 1. And the goal, again, is to bring us closer to being rainbow. So the first type of move that we can do is maybe we have a sign that's not like under an arc. The sign needs to be under all of the arcs, otherwise we won't have this consecutive interval in the middle. So if we have such a situation where a sign is sitting at like position I to the left, like here, and then it has this sort of starting arc at I plus 1, well, we can just swap so that it lands under the arc. And then there's a similar sort of symmetry. Well, if we have an ending arc here, and then we have a sign that's outside of that arc, we want to bring it inside the arc. And so we just do this little swap so that it's inside the arc. So this is what TI does in these situations. Okay, so that's one way we can get closer to rainbow. Another is we might have two arcs that are butting up next to each other. So one has an ending arc at position I, and one starts a new arc at position I plus 1. We need eventually all our arcs to be as nested as possible. And like right now, they're not. So the only way to be able to get one arc to go under the other is to have this crossing happen. We have to have a crossing in order to move one arc under the other. And so that's what happens here. If you have two arcs next to each other and you act by TI at position I, you can cross those arcs. We can also uncross arcs in a certain way. And again, these crossings, they might feel a little bit unlocal, and so we really have to be careful that the uncrossing is only allowed to happen at I if the corresponding next arc starts at I plus 1, for instance, in this top picture. So we have these adjacent starting positions, we can uncross. Similarly, if we have adjacent ending positions, we can just uncross. So again, that's getting us closer and closer to being this nice nested rainbow. There's another type of move, which is eventually we want all of our signs to be the same sign. And the way that we can do that and preserve this parity that we need with the number of minuses and number of pluses in P minus Q is we can create an arc by taking opposite signs and joining them up together. And we can do this when these signs, again, are in adjacent positions at I and I plus 1. Now, we can also try to act by TI if we're not in one of these situations, but it wouldn't bring us closer to rainbow. And so what we say is that in the other cases, just do nothing. So if you're not going to get closer to rainbow, do nothing. Okay. So what we've really got here is like a nice hecka action on this set of clans. So by construction, if you do this thing twice, like if you've already gotten closer to rainbow, you're not going to get any closer by doing something else at that same spot. So TI squares to I. You can check that the braid relations and the commutation relations hold. And because we have these braid and commutation relations holding, we can have a well-defined operator corresponding to any permutation in the symmetric group. If we have a reduced expression of W as a product of simple reflections, we'll define the operator TW just to be the corresponding composition of those TIs. Okay. And again, it doesn't matter because the braid and commutation relations, we could have picked any reduced expression, and we get the same ultimate operator in the end. All right, so here's just an example to summarize a bunch of the different moves that we saw. So for instance, here at T2, we can uncross. Here, if we apply T4, we're joining these arcs. If we apply T7, we're bringing the sign in under this, we apply T7, if we start here and apply T7, we're doing nothing. And then T6, which is looking at 6 and 7, is going to take that plus and move it in under that arc. Okay, so have we sufficiently internalized the moves? Yeah. All right. So Weiser's setup involved taking certain pairs of inverse Grassmannian permutations. So U is going to be P inverse Grassmannian. V is going to be Q inverse Grassmannian. We need P plus Q to be equal to N. So we actually care about what flag variety we're computing cohomology in. And then we have this additional condition that U is less than or equal to W naught V. Secretly behind the scenes, we're looking at an intersection of of a Schubert variety and an opposite Schubert variety, and this is the condition we need to have a non-empty intersection. And the idea is that we're going to associate a clan to these two inverse Grassmannian permutations. In particular, it's going to be a non-crossing clan, and we're going to look for permutations in Sn really of the right Coxeter length, so that when we act by this operator Tw on this starting clan, we reach the rainbow clan. Okay, so how do we define this starting clan? So we have a unique non-crossing clan for each pair satisfying these hypotheses, and we construct it kind of by these 4 cases. So roughly you should be thinking, well, if U of I and V of I are both small relative to P and Q, we're going to start an arc at that position. If they're both big relative to P and Q, respectively, we're going to end an arc. If P is big and Q is not, then we're going to have a minus sign. If Q is big and P is not, then we're going to have a plus sign. So looking here, for instance, like 1, we have that this, at position 1, we have 1 is strictly less than 4. So this is small with respect to P. We have that 4 is greater, so I'm mixing up my inequalities here, but 1 is, there we go. Okay, 1 is less than or equal to 4, and we have that 4 is strictly greater than 3, and so we're going to get a plus there. Here, for instance, at position 2, these are both small relative to P and Q respectively, so we start an arc there. Are there questions about this construction? Yeah. So this is something that will always get, wait, can you repeat the question, Swan? Yeah, is there an obvious way to see that there's always as many starting arcs as ending arcs? There's definitely something to work out, and this is part of the content of what Weiser did. But it's like on the level of a lemma, but maybe not a lemma I'll get right now in the moment. Yeah. So you shouldn't be looking at this and saying, oh yeah, I immediately understand that this is well defined. I'm saying, yeah, take it on trust that this is going to be okay. Yeah. And I like that question, how it leads to later, like how can you know that there's the same number of pairs? We'll see a different sort of situation where like we're just fine. Okay, so the theorem of Weiser is that if we fix U, V, W in SP plus Q, so that U is P inverse Grassmannian, V is Q inverse Grassmannian, and U is less than or equal to W naught V, so W naught is this permutation N minus 1, and so on. So the longest permutation in Sn, or Sp plus Q. Then the Schubert structure constant is either 0 or 1. So we have basically this multiplicity freeness going on. So in contrast to the situation of Littlewood-Richardson tableau, we could have a whole lot of them. We could have really, really high values for these coefficients. But here, always just 0 or 1. So then our job is just to pick out when is this coefficient 1 and when is it 0. And so the content of Weiser's theorem is that, well, this coefficient is 1 if and only if we act by TW on this starting clan, and we get to the rainbow clan, plus this, this dimension consideration that we need length of U plus length of V to be equal to length of W. Otherwise, if this isn't satisfied, like, we know automatically that this coefficient is just 0. So that's Weiser's theorem. And let's look at an example. So here, I'm going to take just like 2 copies of the same permutation. So these are both 2 inverse Grassmannian. You can see that the 2 is out of order with the 3. We have this starting clan here. Maybe I'll crowdsource. Anyone spot a move that I can do? Yeah, I can swap the 2 and the 3. So now I'm going to get this cross. And I'm going to remind myself that that was a T2. What else can I do? I heard like, wait, say it loud. Yeah, so we can turn this crossing, we can like now uncross. And this is a little bit tricky because there were actually 2 different ways that we could have uncrossed, even though it's the same picture. We could have uncrossed at 1, or we could have uncrossed at 3. So it's a little bit funny that we can apply the same operator and we can get the same picture out, but these count as 2 different paths that would have led to the rainbow clan. So in particular, we get this picture here, and then this tells us that we have 2 non-vanishing Littlewood-Richardson coefficients, or Schubert structure constants for this example. You have to kind of read the paths backwards. So we had a T1, T2 because of how we are composing functions. We're starting by acting on T2, or starting by acting with T2, then we act with T1. Or we could have had this other path, T3, T2, that gives us that word. And in particular, yeah, these coefficients are non-vanishing. We applied all the different rules that we could get. We didn't find any other permutations that got us to the rainbow clan. So these are the only non-vanishing Schubert structure constants with U and V as their subscript. Again, with U, V, W all being in S4. Questions about this example? Yeah. Mm-hmm. Yeah, so yeah, if we have, if this condition fails, like you might have that some moves do nothing. You might also, if W is just too short, like you would never get up to rainbow, but that, yeah, that doesn't really involve the condition. But exactly. Yeah, yeah, yeah. Okay. Yeah, I believe so, yeah. It comes from like these clan moves are really telling you things about like Bruja order in K orbits. And so you have to have some correct codimensions there. And yeah. Uh-huh. Yeah, like you can expect to find the length of the word just from being like U plus V, and then if it's, or length of U plus length of V, and then if you get anything else, like this combinatorics isn't going to line up the way you want. Yeah, you'll either be too short or you'll be taking steps where you're doing nothing. Yeah, and this is like by how these were constructed, and again by the geometry that Weiser was working in. Yeah. Okay. All right. So these hypotheses that Weiser needed in order to work inside of this geometry, they're kind of restrictive. So for instance, if U is 2, 3, 1, and V is 2, 3, 1, so this is really, we're multiplying x1 by x1 in Schubert polynomial. Oh wait, sorry, we're multiplying x1, x2, and squaring it in Schubert polynomial land. Yeah, we can't do this in Weiser's setup. We have a problem that P equals Q equals 1, but these permutations live in S3. They do not live in S2. P plus Q is equal to 2. it's too small for these permutations. So we're sunk. We can't compute with this rule. And again, yeah, at the level of Schubert's, we even run into another problem, which is when we multiply these two Schubert polynomials, in this stabilization picture, we end up with a Schubert polynomial that's indexed by a permutation in S4. And so we can't ever pick up that corresponding Littlewood-Richardson coefficient if we just pretended that 231 was 2314 instead. So that's a little sad. There's another way that the hypotheses are just kind of too restrictive for us. And this is this thing about this condition that U needs to be less than or equal to W naught V in the Strong-Bruchau order. So here for this small example, we have U equals 213, V equals 312, P equals 1, Q equals 2. So it's fine. They're both in S3, which is 3 is 1 plus 2. So that's okay. But W naught V, so we basically just reverse that string. Oh, wait. Yeah, what did I do? Anyone gonna save me? Okay, we swapped, yeah. I got my lefts and my rights a little mixed up like midway. So I'm gonna trust previous me and hope that this is okay. But the point is, in this example, we end up with two things that are actually of the same Coxeter length. So like they're gonna be incomparable in this Bruchau order since they're different. And I've even drawn the Strong-Bruchau order on the side for your reference. So this one does not fall within this situation where we can use Weiser's setup because in the secret geometry we have an empty intersection of Richardsons and we're just like sunk in the water. There's no structure there that we can leverage. So at the level of Schubert's, this computation looks like I want to multiply x1 times x1 squared. And we can't do this with this setup. So yeah, it's a little bit sad. But we can play combinatorial tricks and we can soup up Weiser's rule to get a whole bunch of other stuff. So how do we fix this? We're gonna fix it with a bunch of cheap stabilization tricks. So if we have U, V, W, and Sn, it's a fact that the Schubert structure constants satisfy these equalities. So if we just include all of these permutations into the next symmetric group up, the structure constant stays the same. And then if we do this sort of like little back stabilize-y looking thing where we prepend to 1 and then shift indices. So for instance, we might take 3, 1, 2. We might map it to 1 and then 4, 2, 3. So we're just prepending and then adding 1 to all the remaining entries so that we get a permutation again. If we do this stabilization thing, then the Schubert structure constant stays the same. Okay, so what we can do is we can go back to this example. So in this one in particular, we were sad because P plus Q equals 2, and that was less than 3, and there was no way of forcing U and V to live in S2. So what we can do is we can prepend. When we prepend, what's happening is we're shifting P and Q a little bit. So we get a new like P prime equals Q prime equals 2. That's okay. This prepending plays very nicely with left descents. And then these are living naturally in S4 now. And that's great because 4 is 2 plus 2. Yeah. Mm-hmm. So if you start with a known structure constant like this, and then you prepend, you do get this equality. But then the thing is, you'll get more Schubert structure constants over here that are also non-vanishing. So the top, you can get a bunch of different stuff going on. Yeah. So there's ways of seeing this, like either from, like, I don't know, I like to think in pipe dreams, and so there's ways of seeing this in pipe dreams, but there's also just like a whole bunch of algebraic things that you could do, or geometry. Yeah, and at some point I have a citation to Bergeron-Satilli for another stabilization trick. There's all sorts of ways of thinking of chains in Bruchau order that are going to give you equivalent Schubert structure constants. This also is a parallel and maybe a hint to what's coming next in this talk, but Dave was talking about this back stabilization yesterday, and this back stabilization that you got no new structure constants basically in this way, like all the Schubert structure constants are living in this world. So this is just a cheap sort of trick that you can do, and the coefficients agree. Exactly. Yeah. Yeah, I think that was one way that we very fast verified our statement when we were thinking through the, yeah. But again, the statement, common statement, yeah. Okay. So yes, how do we fix this? We prepend. Now these are living at least in the right symmetric group. But there's more stuff that we have to check. We have to check this W naught thing. And 1 cross U is unfortunately not less than or equal to W naught 1 cross V. And so we might think, oh, we're sunk again. What are we supposed to do? Well, let's just try back stabilizing again. Okay, so we do that. Now we've got P double prime and Q double prime are 3. Oh no, we're laughing, right, because we're in S5 and not in S6, and how unfortunate. Oh, what did I do? Oh no. Oh, yep. Thank you. 1, 2, 4, 5, 3. Yep. So we're laughing because this wasn't a permutation. Okay. Thank you. It's how I know that you're still awake. I plant these typos just for, yeah, because, yeah. Okay. So unfortunately, these are living in S5, and 5 is not equal to 3 plus 3. Anyone, can we spot a way to save us from this sadness? Yeah, we can just add a 6. So this is the easy stabilization. We can just include these into S6. Okay. So we do that. We get this picture here. Now we're in this situation where we can use Weiser's machinery. So we have an honest-to-goodness, well-defined starting clan. We can play this game. We can try to get to rainbow. We can look for Schubert structure constants. We'll get a bunch more Schubert structure constants now, potentially. But in particular, if we do a bunch of index shifting, we'll be able to get back to the original coefficient that we wanted to know about. Now, as you can tell, I'm not good at reindexing. Reindexing sounds terrible, so let's not do that. Instead, let's just let ourselves work with negative numbers. So again, this back stabilization idea, let's not reindex all the time. Let's just allow ourselves to work with permutations of SZ. So we should be, working with these permutations in SZ. This leads us to a notion that Oliver and I defined of backstable clans. Okay, so what's a backstable clan? It's going to be very similar to a clan, but now we're not scared of 0 and negative numbers. So we're going to have partial matching on Z. Unmatched numbers are assigned a plus or a minus. And then we have this condition that eventually we have just all these nested rainbow-like arcs. So eventually there's some I and J, so that I minus K is always matched with J plus K for all K in positive integers. So I've drawn kind of with these dots, like so, these dotted arcs. Now you might worry, how do we draw this infinite picture? Well, in practice, we never have to, because really this I and J gives us a little window in which we can think about this infinite clan as just being a finite clan. And in particular, if we have a finite clan, we can just think about it as being backstable by just adding as many matchings as we want to fill it out to this infinite picture. So these are really just capturing this window of this combinatorics, but now we don't have to care so much about P plus Q being equal to N. It doesn't matter. Now we don't have to worry so much about what if this arc doesn't have a friend to match with. We can just keep reaching over this way and that way and match everything up. So really, this is the more natural combinatorics to be working with in this setting. Okay, so we define the starting clan in the exact same way as before, but now we're looking over all integers z. Or in z. So we have this non-crossing PQ clan. The P and the Q is still going to tell us about number of pluses minus number of minuses. We're going to form these starting arcs, ending arcs, minus pluses in the same way. So looking at our example from before, I've drawn just part of the clan so far. This is what would have happened had we tried to just take a clan and not stabilize it all. We wouldn't have found those matchings that like Swan was asking about. But now what we can do is like have more numbers and then it's all fine. So really like this is saying like 0 maps to 0, -1 maps to -1. We just have this infinite permutation, but inside of it is living our like finite permutations that we're really interested in. And then we get this starting clan here. You'll notice it has the same exact shape as the clan that we saw before, but it's just shifted. And that means that we don't have to unshift. We just like are where we want to be in the first place. So I hope that I'm convincing you that backstable clans is the combinatorics that we want here. Yeah. So the W naught condition we no longer care about. It is. Oh, thank you. Yep. That's copy paste. Okay. Yeah, it's gone. We no longer care. Excellent question. Gone. Okay. So, yes. And here we have the theorem with Oliver that says, okay, I've kind of like put in pink the things that changed from before, and you'll notice not very much changed. So we drop this condition. This U is less than or equal to W naught V is no longer relevant to us. W naught doesn't even make sense if we're not in a fixed symmetric group. Okay. But we still have U as P inverse Grassmannian, V as Q inverse Grassmannian. We want U, V, and W to really be like permutations of positive integers if we want to work with just like ordinary flag varieties. And so we still have this multiplicity freeness. And this coefficient is 1 if and only if we can act by TW, same moves as before, on this starting clan to get to our new rainbow clan. And again, the rainbow clans are just what you think from before. We have this interval of consecutive signs, and then all of the same sign, and then like we have these arches surrounding them off, but now to infinity. Okay, so in our example from before, we look at this, this is a different example now, but we look at our starting clan, and then we can apply T1, for instance, to get this crossing. Then we can apply T2 to uncross those two arcs. But now, because we're just interested in permutations of SZ+, we're only going to allow ourselves these positive indice TIs. So I'm not going to care or look at the T0 to do this uncrossing. Okay. So here, we just get this one non-vanishing Schubert structure constant, which is good because if we take x1 times x1, we get x1 squared. Perfectly lovely Schubert polynomial for 3, 1, 2. Okay. So now we have this rule, and our main motivation for getting into this world was actually like not this particular rule, but we were interested in studying derivatives on Schubert polynomials and seeing what it got us. And so in particular, we used some derivative tricks which started to convince us that inverse Grassmannian permutations are particularly nice to look at. Okay, so this was homework for a lot of you, but we have this operator. We can sum up these partial derivatives and get this Nabla operator. And the theorem with Zach Hamaker, Oliver Pechenik, David Spire is that if you apply this operator to a Schubert polynomial, you get a sum over SKW less than W, K times the Schubert polynomials for SKW. So here's an example here. And remember, for these left descents, we should be thinking about like, well, 1 is out of order in the string with 2, so I can flip them. The price that I pay is a 1. 3 is out of order in the string with 4, so I can flip them, and the price that I pay for that is a 3. And I've actually done out the calculus and maybe done out the calculus correctly. We'll see. And then regrouped them by their corresponding Schubert polynomials, and we get this thing here. Okay. So the proof that I was hoping that you would do is to check that this operator commutes with divided differences and then use induction. So that's a very simple proof. I wanted to just give a non-simple proof just because I like it. It's not hard. It just requires more machinery than is strictly necessary for this. This is maybe like, this is maybe going to be a very fast non-simple proof. But you can take this Cauchy identity for double Schubert polynomials, which expresses a double Schubert polynomial as sums over length additive factorizations of W into products V times U. You get this piece that's an ordinary Schubert polynomial in X's and an ordinary Schubert polynomial in Y's, and you sum up a bunch of products like so. So what you can do is you can take the length of W minus 1, comma 1 degree part. So look for all the degree 1 and Y's, and extract these from both sides of this equation, then set Yi equal to 1 for all I. So the left-hand side, it's clear from the combinatorial formulas that we have, like pipe dreams and bumpless pipe dreams, where we have products of a bunch of binomials being summed up, that we really do get the result of this derivative operator. So that's maybe something to check, but you can draw some pictures like I've done here and see that, like, as we're picking which Y we're going to pick out of this product, it's telling us an X that has to go away. And that's like what differentiating is doing for us. On the right-hand side, the only V's that are going to give us the right degree are simple reflections. And in particular, simple reflections so that we go down in left weak order. That's what this length additive is getting for us. If we specialize this Schubert polynomial to 1, we get K, and then that's giving us this right-hand side of the expression. So this proof is maybe gratuitous, but I just like how closely connected this formula is to the Cauchy identity. Okay, and then you could ask for like combinatorial proofs, and for instance, Hugh Denon, I think, is going to give us a lot of those. I'm going to tell you just about one special case in terms of taking derivatives of Schur polynomials. So Schur polynomials, of course, are a special case of Schubert polynomials. In this case, we have like a formula in terms of just taking away corners of partitions. So we get some indices like so, and then we're summing over ways to take away corners to get a new valid partition. And a combinatorial proof of this involves just jeu de Tacan. So it's connected to a very fundamental combinatorial procedure. So in this jeu de Tacan, to remind you in case you've not seen it, what you can do is you can start with a semi-standard tableau, and you can rip out a box. So often people will rip out this box in position 1, 1, but you could rip out like whichever box you want. And then you start doing these little local slides that preserve semi-standardness. So along rows, we want to be weakly increasing. Along columns, we want to be strictly increasing. And so we just like do these little slides. So here, for instance, 6 is less than 7, so it has to slide up. Otherwise, we'd be out of order. Here, like this 9 can slide over. Here, this 10 can slide over. And then we get, ultimately, this tableau out of this procedure. Well, what's going on here with Schur polynomials is one way to think about derivatives is we're like lowering each thing in our monomial by 1. So like if we have like x1, x1, x2, normally we'd write it like x1 squared, use our product rule. But we could think about this as omit the first x1, omit the second one, omit the x2. Add those up, we're taking derivatives. So combinatorially, it means we need to take each of these semi-standard tableaux, and we need to omit the entries in all possible ways, and then hopefully resolve to semi-standard tableau. And what you'll find when you do this is we get the right tableau that we're expecting with the right multiplicity just by resolving by doing jeu de Tacan. So again, this formula, it has some nice algebra, some nice combinatorics. It's like there behind the scenes governing some structure. Okay, And then another thing that was homework and another typo on your homework, I forgot this length of W factorial, so some of you pointed that out, and thank you. But you can use this to get a very, very short elementary proof of Macdonald's identity. I'll probably skip talking through this slide, but it's very, very simple just by thinking about the difference between taking derivatives of monomials and the difference between traveling down these weighted Bruhat order chains. Okay. So what else can we do with derivatives? Well, we can take derivatives of products of things. So I'm going to give you this proposition, and then I very meanly didn't put the proof down, and the proof almost makes more sense than the proposition, so now I'm going to just show it to you. Okay, so the idea is we're going to multiply two Schubert polynomials and expand in the Schubert basis. What we can do is we can take derivatives of both sides of this equation. On the left-hand side, we should have the product rule. Nabla, Schubert, V. Okay, sorry. Worst math frac S's ever. On the left-hand side, we have the product rule. And on the right-hand side, just by linearity, this operator moves on in. And so we can apply this formula from before, and we can go down our chains in our weak order. And then we extract the coefficients of the Schubert polynomial for W from both sides. And what we end up with is this thing here. So these i's are telling us, well, I stepped down in SI. And these j's are saying I stepped down SJ. Over here, to keep the degrees even, we're stepping up with SK. And so we get these linear relations among Schubert structure constants. Okay. As a corollary, again, by using stabilization, we can actually drop a lot of these coefficients. But the price that we pay for dropping these coefficients is we get this extra coefficient, which is sometimes just 0. In particular, if we stabilize this again, we wouldn't find anything new. So eventually, this kind of evens out, and there's nothing new to find. So we get this system of two linear equations in some number of variables. Now, this is in practice, just a lot. It's a little bit of a mess. There's a whole lot of coefficients floating around. But the easiest case is for inverse Grassmannian permutations. For inverse Grassmannian permutations, we have just two things on the left-hand side, because there is only one way to step down from U and only one way to step down from V. And then we do have a bunch of stuff on the right-hand side, but that's okay. We understand the right-hand side due to clans. We can use our backstable clan rule and understand what all these coefficients are. So what we really have is a system of two linear equations in two unknowns, and that's good news for us. Okay, so this leads us to a combinatorial rule in terms of almost rainbows. And let's see, I guess Alex told me I could have, okay, I'll try not to go too long. I could go into maybe too much proof, but I promise not to. So I'm going to state this almost rainbow rule. So again, it looks very, very similar. We have permutations U, V, W of positive integers. U is P inverse Grassmannian, V is Q inverse Grassmannian. Now here, I've added this SP. So we're able to multiply SPU's Schubert polynomial times V's Schubert polynomial and see what happens. Now, this product is still multiplicity-free somehow. So that's nice. Moreover, we can pick out when the coefficient is 1. It's going to be similar, but I'm hiding some things and some notation here. So we're going to act by TW on the same starting clan as before, but now we're going to hope that we land in some specified set of things that we call almost rainbow clans. There's also this codimension condition here in terms of these Coxeter lengths that must be satisfied. Okay, so this set is a set of almost rainbow clans, and the set doesn't depend on U and V at all. It depends just on P and Q. Okay, so a clan is almost rainbow if it's not rainbow, but you just apply one TI and you reach rainbow. That's all that means. So for P not equal to Q, they look kind of like this. You could uncross, you could move things under. For P equals Q, we have this funny middle thing where we could like connect a minus plus to an arc or connect a plus minus to an arc. Now, for p not equal to q, for reasons we want like just these ones, but not things where if we were to act by tq, we would go up. For p equals q, we have some sort of rule like this, where minus plus is okay for some reason, but plus minus is a no-go. So it's some subset of almost rainbow clans that we're aiming for. And then, yeah, so the idea of the proof is to use these linear relations and solve these equations. I'm not going to go through the gory details here. There's, a lot of gory details. But you can use more stabilization tricks. The really hard case was when p equals q. We run into this linear dependence. And, well, we just couldn't solve a linearly dependent system of equations. We could only guess. But you can do more weird stabilizations and reduce it to p not being equal to q, to the situation there. OK. So next steps, how far can we push these linear relations? What about almost rainbows? There's a lot of them, but you could try to extract more rules. And can we say anything about these k-theoretic structure constants in terms of these clans? Okay, so thank you so much.